Energy harvesting wireless networks with correlated energy sources, presented at WCNC 2016 and awarded MacTrack Best Paper Award. The outline of the presentation is as follows. Due to the tremendous increase in the number of battery-powered wireless communication devices over the past decade, harvesting of energy from natural resources has become an important research area as a means of prolonging lifetime of such devices. The main challenge is that the energy arrives at random times and in random and minuscule amounts. There is a vast amount of research on how to best manage networks with this random energy source. The main body of research lies in the areas of scheduling and routing strategies and also channel access strategies. Energy harvesting processes are often correlated. Depending on the spatial distribution of each devices, the amount of energy harvested by different devices is typically correlated. For instance, consider equipped sensors planted in a highway. The sensors on the same lane exhibit high positive correlation, meaning that they are more likely to harvest the energy at the same time, while the sensors planted on the far apart lanes exhibit no correlation at all. So the question that comes to mind is that can this knowledge help in coordinating the transmissions? We develop and analyze a simple threshold-based transmission policy, which grants access to an EH node only when its battery state exceeds a given threshold value. Threshold values are selected based on the battery capacities and the correlation among the EH processes of the nodes to maximize the long-term throughput of the system. Moreover, thresholds strongly depend on the level of correlation. We adopt an interference model where the simultaneous transmissions of two H nodes result in a collision and eventual loss of transmitted packets at the base station. Each node is capable of harvesting energy from an ambient resource and storing it in a finite capacity rechargeable battery. EH nodes have no additional power supplies. The nodes are data backlogged, and once they access the channel, they transmit until their battery is completely depleted. E subscript n of t is the energy harvested in time slot t by the node n. We assume that the energy process is an independent and identically distributed Bernoulli process with respect to time. However, at a given time slot, energy harvested by node 1 and node 2 may not be independent. We adopt a deterministic transmission policy in which the nodes access the channel if their battery level is above a certain threshold denoted by gamma. Moreover, we assume that there is no central coordination unit and there is no feedback provided by the base station to the nodes. We assume that whenever a node accesses the channel, it transmits with all the energy in its battery. One downside of this policy is that it may suffer from collisions. Node 1 successfully communicates with the base station if upon transmission, node 2's battery state is below its threshold. Consequently, the rate of successful transmissions of the nodes denoted by R can be calculated as follows. We aim at maximizing the long-term average total throughput by choosing the transmission thresholds intelligently, taking into account the possible correlation between the EH processes. We model the joint battery states of the EH nodes as a two-dimensional Markov chain. In the following theorem, we show that the probability of being at any state equals 1 over gamma 1 times gamma 2. The theorem assumes that all states are visited. Interestingly, although the EH process is correlated, the discrete time Markov chain has a product form stationary distribution. There is an important trade-off in calculating the optimal aggregate throughput. Since the rate is a concave function of the thresholds, it is better to transmit small packets by choosing small thresholds. However, small and frequent transmissions suffer from collisions, so it is better to transmit large packets rarely. The optimization problem is difficult to solve since the optimization problem is a non-convex integer programming. Hence, in the following, we obtain optimal solution for two important special cases. These special cases are as follows. In case 1, both EH devices are acting oppositely, which we denote by high negative correlation. This may happen when, for example, one sensor is located at tidal troughs while the other is at the crest. The second case, which we denote by high positive correlation, corresponds to the case when both EH devices are spatially close. For high negative correlation case, at any given time, the energy may be harvested by only one node. We assume that node 1 harvests the energy with probability p, whereas node 2 harvests the energy with probability 1 minus p. For this case, the aggregate throughput is calculated as follows, where delta is the noise and transmission time normalized energy harvested per each EH event. For this case, it can be shown that optimal thresholds for both devices are both equal to 1, meaning that each EH device transmits whenever it harvests a single unit of energy. It is worth mentioning that the optimal thresholds prevent any collisions between the transmissions of EH devices. For high positive correlation case, either both EH devices generate energy or neither of them does. We assume that the energy is generated with probability p. In the case of high positive correlation, only a part of the state space is visited. In order to better illustrate this case, consider an EH network with thresholds gamma 1 equal to 4 and gamma 2 equals to 6. The state space of the corresponding DTMC is given in the figure. Large solid and empty circles represent visited and unvisited battery states, respectively. The solid lines represent the transitions of battery states when thresholds are not yet reached, and the dotted lines represent transitions when at least one of the nodes transmits. Also, arrows shows the direction of the transitions between the states. Since only a subset of the state space is visited infinitely often, the average throughput calculated in the Markovian framework is no longer valid. Hence, we calculate the aggregate throughput for this case in a different manner. Due to our transmission policy, EH node n transmits whenever its battery level reaches gamma n. Note that both nodes reach their respective threshold simultaneously every LCM gamma 1 and gamma 2 instances of EH events, where LCM denotes least common multiple. Since they transmit simultaneously, a collision occurs and they both exhaust their batteries, that is to say, they joint battery state transitions into state 0, 0. The process repeats afterwards, hence the renewal period of this random process is LCM gamma 1 and gamma 2. In every renewal period, each EH node n makes LCM gamma 1 and gamma 2 over gamma n minus 1 number of successful transmissions. Hence, by using renewal reward theory and noting that on the average a unit of energy is harvested in p proportion of time slots, we obtain the following throughput for each EH node n. For case of high positive correlation, we consider two cases for the harvested energy. Either delta is small, which means that the rate term is linear with thresholds, and thus optimal thresholds minimizes the number of collisions. Therefore, it is optimal to choose the thresholds as large as possible as long as the greatest common divisor of gamma 1 and gamma 2 equals to 1. When delta is large, optimal thresholds has a different structure. Since the objective function has the property of diminishing returns, that is to say, the rate of increase in the function decreases for higher values of its parameters, each device will choose transmitting more often, equivalently short messages, using less energy. However, transmissions are scheduled every time each node exceeds the threshold, which dictates the small thresholds. When both EH devices transmit with small thresholds, there will be a large number of collisions, so it can be shown that the aggregate throughput is maximized when one EH device transmits short messages, whereas the other transmits long messages. Here, we evaluate our analytical findings through numerical results. We consider the capacity of the batteries for both nodes to be 10. In the following figures, expected throughput of the network with respect to the thresholds are illustrated. It can be seen that optimal threshold for high negative correlation case is 1 for both nodes. In the case of high positive correlation, when delta is large, it can be seen that the throughput is maximized when one threshold is the smallest while the other one is as large as possible. We have investigated the effects of correlation among the EH processes of different EH nodes as encountered in many practical scenarios. We have developed a simple threshold-based transmission policy to coordinate EH nodes' transmissions in such a way to maximize the long-term aggregate throughput of the network. In the threshold policy, nodes have no knowledge about each other, and at any given time they can only monitor their own battery levels. Considering various assumptions regarding the EH statistics and the amount of the harvested energy, the performance of the proposed threshold policy is studied. In case of high negative correlation, we proved that it is optimal to transmit whenever a node harvests a unit of energy. In case of high positive correlation, however, we saw that collisions are inevitable. Thus, the optimal policy chooses the thresholds to balance the number of collisions and logarithmic transmission rate. As of future work, generalization of results to more than 2 nodes and to other transmission policies taking into account feedback should be investigated.